No, race. Did that? Yeah. Okay. All right. So we've got to finish 2-2 and then start 2-3, and so that we can get through as much as possible, we're just gonna dive in. So in 2-2, on Wednesday, we did some examples of essentially if we were given an original function, can we pick out its derivative graph from some choices? And we still need to talk about essentially the other direction. So we're going to talk about the other direction. We're going to do one example of that and then move on to 2-3. So first thing is that I want to write down, let me reshade this one last time. So the first thing is I want to write down kind of those steps like we did for the other direction. So say we want to determine the original graph given a derivative graph. It's kind of the opposite of what you do in the other piece. So instead of looking at maxes and mins, we're going to look at the zeros of the function. So that means where it's going to touch or possibly cross the x-axis. Now, I didn't catch this when I was writing these notes for some reason. While you can consider, you can't hear anything. Testing. Yeah, I hear myself. So, or see anything. Oh boy. Oh boy. All right, so I'll let her have 1 second to pop out of here and then pop back in. But I'll talk about something while she's doing that, hopefully. So, okay, she popped back out. But if I keep babbling, then she'll know if she can hear me. So I forgot when I was writing these notes for some reason. While we can talk about where it touches, can you hear me now, Ami? Let me reshare just to try to make sure that's going through as well. Babble, babble, babble. Babble, babble. Testing, testing. Babble, babble. Mommy. So while we can talk about where it touches the x-axis, the main thing we're going to focus on is where it crosses the x-axis. So I'm going to kind of cross out that part where it says touches, and we're going to focus on where it crosses the x-axis. Oh, yay! It just seems to be a bug sometimes. Okay, so we're going to locate the zeros of the function, and we're going to focus on where it actually crosses the x-axis. So I'm kind of crossing out that part where we can talk about where it touches the x-axis. Those kind of are points of interest, but not the ones that are actually going to tell us anything important. So at these points, the original function is going to have either a maximum or a minimum. At this point in time, we don't really know which one. We'll find some skills in a couple sections that'll essentially help us figure out which one it should have been. But we don't really care if it's one or the other. We just care that it's either a max or a min. So sometimes, just like last time, sometimes this is enough. But sometimes you need kind of this second step to go further if you need to. So then what you would do is you would determine where the derivative, so the graph you're given, is positive and where it is negative. And this is where we kind of call upon that relationship between the two types of functions again, because this is going to tell us where the original function will be increasing and decreasing respectively. Pretty much 100% of the problems we will look at are solvable in those first two steps. In general, you might need more, but in terms of the stuff we'll need, that will be enough. But without more information, we couldn't really know what the function is doing above or below the x-axis, just like last time. But we can look at the y value of the derivative graph, the one we're given, to kind of figure out how steep the original function should be. Should it be increasing very quickly? Should it be decreasing very quickly? Or doing it in a very slow manner? So we could use kind of that extra information of the y value to kind of get us some extra information, but we usually don't need it. And by usually, I mean like never for this class. So I'll leave that up for like 5 more seconds. So y'all can get it down. We'll do one example of that. It's a very similar idea to the other ones. It's just kind of working in the opposite direction. And then we'll head on to 2, 3. So a couple more seconds. All right. So put this over here. So we've got, let me zoom in a little bit. And I know the choices are kind of blurry. Sorry about that, but we don't necessarily need all of the it to be any clearer. So this is kind of, again, backwards to what we were doing before. So instead of looking for maxes and mins, we're looking for the zeros of the function. We're looking for where it crosses the x-axis. Now, technically, it also crosses back here at kind of the very end of the function. That's not really going to help us at all because it doesn't tell us very much because we don't see what's happening afterwards. But technically, it does touch the x-axis and kind of cross there, so I'll circle it as well. But the main two we're going to focus on are going to be these two. So the first thing we can then think about is, now this way is, I don't want to say more complicated because it's not, but I think people get so used to going the way we were going the other day that they then make this a bit more complicated than it needs to be. So what we want to do here is we essentially want to break the graph up at -3 and approximately 2. And what we would need, whoa, I really need to figure out what makes it do that. So essentially what we would want to do is we want to go over to our choices and kind of break those up at that point too. Now again, I know that these are kind of blurry, but this would be at -3 and this would be to -3 to -3 2. Now the thing we want to happen at kind of those lines that I just drew is, since the derivative is 0 at those points, and again it's kind of 0 at this point back here, but since it's so close to the end of the graph, it's going to be harder to use. So we'll just focus on those middle two. Is we would want the graph we're trying to choose from to have a maximum or a minimum there. Well, A kind of has a max, but it's farther back than it should be. But just for giggles, let's just keep it in the running. You know, maybe we didn't approximate the 0 well enough or something like that, or the fact that this is super blurry maybe throws it off. I don't know. So let's keep A in the running just kind of for giggles, even though you can kind of cross it off because that maximum isn't at the right point. B looks like a really good option because both of those lines that I drew definitely go through a maximum or a minimum. So that one looks like it's probably going to be the best bet. And then C, if I want this to be the original function, I would have had to have maxes and mins at these 2 points, but I don't at all, and they're nowhere even near that. So we can definitely cross C off, because anywhere that the derivative crosses the x-axis, I need a max or a min of the original function. So say we weren't sure whether to kick A out of the running or not, so we needed a bit more information. Well, now we wanted to look at kind of that relationship between the two types of functions we have going on. So since we have the derivative, we're going to want to talk about whether it's negative or positive. So in that kind of leftmost piece, that derivative function is negative, it's below the x-axis. And then it changes to being above the x-axis, so it's positive, in kind of that middle piece. And then it's negative again. So if we wanted to talk then about what the original function should be doing, well, if the derivative is negative, then the original function is decreasing. So we're going to want a original function that's decreasing and then increasing and then decreasing. So that's using that relationship between the two functions that we have. Scroll up really quick here. So again, I said that that's really, really important. We use it a lot. I meant it. So scrolling back down. Oh my God, thank you. So essentially, out of these two choices that I kind of have left, which one of them is decreasing and then increasing and then decreasing? Well, the only option that does that is B. And again, we kind of already figured that out from just the first thing. But exactly, Kayla. But with option A, it also kind of makes sure that we shouldn't choose that one because part A starts by increasing. And then it goes to decreasing and increasing. So it's kind of the exact opposite of what we want. And even since we kind of already knew that that maximum wasn't in the right point, this kind of backwards setup, if you will, is what makes it very, very clear that A is not the correct option either. So for kind of this direction as opposed to the direction we were going on Wednesday, look at the zeros of the derivative function. So find where it crosses the x-axis. The points where it crosses the x-axis should then be a maximum or a minimum. You don't necessarily know which type, but it has to be a maximum or a minimum on one of your choices. And then if you need any more information, you look at whether the derivative is negative or positive and use that relationship to the original function being decreasing or increasing to figure out which one of your choices is correct. Questions, concerns on that before I move on to the next section? So I know there was only one example of that one. To be quite honest, this direction is asked less often than the other direction, which is why we did more examples of the other direction. Questions, concerns? I'll leave this up for like 5 more seconds. All right, so let's head over to 2-3 then. So unshare that, and where is 2-3? Oh, no, and this, and in, and up. There we go. All right. So section 2.3 is called Interpretations of the Derivative. Now this is some of 2.3. There's also kind of a second part of it. But part of this is something that we've already kind of seen before, because if you remember, which you'll want to remember if you don't have this relationship kind of ingrained in your brain yet, you're going to want to remember derivative is equivalent to instantaneous rate of change, which is a slope. So since these derivative values are slopes, if we're interpreting a slope, we've kind of already talked about how to do that. We're just going to go into the tiniest bit more depth into it right now. So if you have a function y equals f of x, then the average rate of change can essentially be thought of as a change in y over change in x. You know, we usually write it as maybe y2 minus y1, x2 minus x1, or maybe, you know, f of b minus f of a all over b minus a. But those are technically, another way to write that would be kind of this change in y over change in x, that little delta symbol. I think I've said this before, but this little delta symbol essentially means change in. So I'll kind of put that up there just in case. So if we have that change in x is small, what we essentially have is, well, now I've written stuff in a place where I wanted to write the actual notes. Whoopsies. So if the change in x is small, so the thing in the denominator turns out to be really, really small, nudge, nudge, wink, wink, like something like 0.001, then we would essentially be saying that that's going to give us an approximation. That's an approximation symbol, doesn't look like it. That slope is going to give us an approximation for the derivative. And that's essentially what we were just doing. We were approximating these derivative values with slopes of things that were really, really, really close to each other. And that's what I mean by small change in x, is that the points are really obnoxiously close to each other. So this also implies that for that small change in x, I could also think about it like this. And this is kind of going to give us kind of the setup for the second piece of this set of notes. Now, all I did here was take this denominator and multiply it over to the other side. That's how I got that. Like, it didn't just come out of the air. It's actually kind of taken from the line above, where we just took the denominator of change in x and moved it over to the other side. So this is kind of going to give us a setup for kind of the second half of the note. So it's kind of going to come back in a few minutes. The first thing we have to talk about is this thing called Leibniz notation. So Leibniz notation, so essentially, history lesson. Calculus was kind of developed by two people at the same time. So there was Newton, and then there was Leibniz, and Newton did it kind of in one direction, and Leibniz did it in a different direction. And so we kind of use Newtonian calculus. I shouldn't say Newtonian calculus, they're the same thing, but Newtonian notation. But there's also Leibniz notation. So essentially, we've been writing the derivative as f prime of x. Leibniz notation would write that derivative as dy over dx. Now this is red. I always forget that LaTeX always switches up these little quotes. I don't do that on purpose. It's just the code that I write these notes in. So if I were to read that out, this side over here, I would read that as the derivative of y with respect to x. Now this notation, while it's not entirely required that you use it because both of these two mean the same exact thing, the thing that's useful with Leibniz notation is it makes it kind of easy to determine the units of the derivative. So that's kind of how we're going to use it. We're going to take this Leibniz notation and use it to help us figure out what the units of the derivative are going to be. So the units of a derivative for a function are going to be the units of the dependent variable, which is usually the y, so I'll put y in parentheses, divided by the units of the independent variable, which is usually x. So in other words, if essentially in our Leibniz notation our derivative would to be some dA over dB, then the units of that are going to be the units of A over the units of B, which makes sense because these are slopes and that's how units of slopes work, is it's the derivative, the units of essentially the y's over the units of the x's. But sometimes we don't have y's and x's, so sometimes it can be confusing as to which one is which. So I'll pause for a second. Just in case people need to catch up. These days that I just talk to a screen, I forget that people try to write stuff down as I'm going. So if the derivative of a function is not changing rapidly, near a point, and I'll explain that changing rapidly thing in a bit. So if it's not changing rapidly near a point, then the derivative is going to be approximately equal to the change in the function when the independent variable increases by 1. Now, remember back to a while ago, like one of the first classes, I think, when I was talking about kind of the two ways you could interpret a slope for the first time, and the one way we did it was we essentially took it to kind of be that step idea for slope. If you go over 1, it tells you how much you go up in the y direction. That's essentially what this is saying here, is that if the derivative is not changing rapidly, which again, I'll get to that in a second, we can essentially say that it's approximating the change in the y value per 1 change in x. So it's kind of using that kind of step idea of slope. So what do I mean by changing rapidly? So I have two functions. I have one like that looks like this, and then one that looks like that. Okay, maybe don't go all the way up into that. And say I wanted to look at, say, this point here and this point here. If I were to draw my tangent lines to the best of my ability, so my tangent line of that first one would look something like this, and then the tangent line of this guy would look more something like that. So maybe let me tangent line to remind us which one is the function and which one is the tangent line. Well, tangent line should be the one that's line, but just to remind us if you're looking back at this later. Now, say I take a point you know, kind of next to the point that I drew the tangent line at. For this one, you know, that point is very close to the tangent line. And even if I go in the other direction, you know, it's still, there's a tiny bit of a gap in the other direction, but it's still very close to that tangent line, right? Whereas if I go to the one on the right and I go to, you know, a point kind of next to it, that starts to get farther away. My gap starts to get much larger, especially if I go up to the next one. You know, if I go over again here, I'm still relatively close, but if I go over again on this one, I start to get really far away from my tangent line. So when I say changing rapidly, I essentially mean, is the function increasing very quickly or decreasing very quickly? That would be the case of this one here. It's increasing very quickly, whereas the one on the left is increasing very slowly. So that's what I mean by changing rapidly. So we're going to use this idea of, we're essentially going to be using our tangent lines in a few minutes, and we're going to be using these tangent lines to approximate the function. So we don't know what the equation of the function is, but we kind of want to know where it's at. So we're going to be using the tangent lines to kind of get an idea of where we are. But we need to keep in mind that essentially the farther we go kind of out on the tangent line, the farther we go, the worse our approximation is going to be, because it's possible that the function could start, you know, increasing very quickly and we could start having these really huge gaps. But if we stick, you know, relatively close to the point that we care about, the point that we have the tangent line at, I should say, it would actually give a pretty decent approximation. It might not be perfect, but it could get us like an idea of maybe what the function value is. So we're going to be using our tangent lines to do that in a minute. But back to Leibniz notation really quick. If we want to write down like a value for the derivative, I shouldn't say it like that. If we want to evaluate the derivative at a value, here, let me just write this down. If we wanted to say f prime of 2, how would you say that in Leibniz notation? Now, the kind of bad thing about Leibniz notation is writing stuff like that is not as nice. So the Newtonian notation is much nicer for these, but the Leibniz notation equivalent would be dy over dx. Then you kind of have this vertical line, and then you tell them where you're at. So it's a much more tedious notation for writing down kind of where we evaluate the derivative at, but that's how you would do it. And you do kind of want to be familiar, because sometimes Wiley does go kind of back and forth between the two. So the next main thing we're going to focus on is how to interpret our derivative, which again, we kind of already know how to do, because I've already been talking about interpreting slopes. And we kind of had those two ways to interpret the slope, and it's kind of like now we're just officially going to write it down. So we kind of have been interpreting slopes already, but now let's kind of officially write down kind of how those work. So you kind of have two choices, but you must include three things in your interpretation. In both cases. So we kind of had, which one do I write down first? We kind of have the rate way, I used to call it, and I think I maybe called it the step way. I don't remember what I called it, because I use that one less often. But so we kind of have two choices. If we want to interpret a derivative, we want to interpret a slope. So if you're going the right way, the first thing you want to always state is you want to state the starting x value. So say you're finding f prime of 2 and you're interpreting f prime of 2, you would have to say at x equals 2, or whatever the x context is, at time, at 2 minutes, at 2 hours, at whatever. And then what you do from there is you essentially then need to state the direction. So you need to state the direction, which would be increasing or decreasing. Starting, I do mean starting. You want to state the starting value. So let me just be extra clear there. State the starting x value. Then you essentially need to tell them the direction that you're going in. Are you increasing or are you decreasing? And it's the direction that y is changing by. And you always want to include the y value units. And we'll do an example of this in a second. But whenever I was doing them before, I think I usually said remind them of the y value context. And that's kind of what I mean by this, is once you kind of tell them the starting x value, you then have to tell them, is the y value increasing or decreasing, and what are the units? And then the last thing you end with is you essentially then state the derivative value. With what I like to call rate units. And that's going to be our units of y over units of x. And hopefully what I mean by these will make sense when we do the example in a second, if it's not making sense already. So that's kind of how you lay out the interpretation. If you want to go this rate way, you have to tell them where you start. So after 2 hours, say we're talking about the concentration of adrenaline in the system. You would say after 2 hours, the concentration of adrenaline is increasing by whatever the slope value is. So say it was increasing by 2, what's adrenaline measured in? Milligrams? I don't know, milligrams, say. If it was increasing, you would say the amount of adrenaline is increasing, part 2, by 2 milligrams per hour, part 3. Whereas if you want to go the step way, and again, that's kind of that thing that I was just drawing a few minutes ago, where we're essentially just saying if we jump over 1, how much do we move up by? If you want to go with this way, the first thing you have to do is you have to state the starting x value. Same thing in both interpretations. But then it changes, because the next thing you want to say, so say we were still going with that idea of adrenaline is increasing by 2 milligrams. So say I'm going with this kind of one that I'm just trying to pull out. Adrenaline is increasing by 2 milligrams per hour after, so at, say we're talking about this was some f prime of 2. So let me change this to 3 then, so f prime of 2 equals 3. So you'd state the starting x value, so you'd say after 2 hours. But then what you do here is you essentially state that you add one more x value. So we take that step over. So after 2 hours, increasing the time by 1 hour. So you essentially say you're adding on 1 x value, and then you're going to state the increase or decrease in y values with what I refer to as y units. So in the rate interpretation, you need to use kind of the slope units, whereas in this kind of step interpretation way, you just use the regular y units. And again, we're going to do an example in just a second, so hopefully if that doesn't already make sense, it'll make more sense, because I'm going to write this next one in both ways, and then I'll usually pick one over the other for the rest of them. But if you ever want me to show you the opposite way that I wrote down, just let me know. So I'll leave this up for like 5 more seconds. Let me erase this bit, because this was just pulling that out of the air just to babble a little bit. So if you follow those two kind of setups, you'll always be able to write an interpretation for a derivative value. So that adrenaline one, let me just babble about that a little longer because I kind of, where, let's say adrenaline in the body, we're going to say y at time x. So this would be in hours. That's not how you write hours. And again, I don't remember how adrenaline is measured. Let's say milligrams. This would be in hello pen milligrams per hour. So say I wanted to interpret this idea of it's telling me that 2 hours, the adrenaline in the body is changing by 3 milligrams per hour. I could say that in two different ways. I could say after 2 hours, the amount of adrenaline is changing by 3 milligrams per hour. If I said that, I would be using a right way. Do I have any more space that I can write something else really quick? Not really. I'm going to erase this and rewrite it really quick before I move on. But I could also write the exact same thing by saying after 2 hours, if we increase by 1 more hour, which is poor phrasing, but I'm just trying to get the point across. If we increase by 1 more hour, the amount of adrenaline, come on, pen, will increase by, abbreviating because I'm running in a space, 3 milligrams. And that second interpretation would be essentially this step way, where I say after 2 hours, if I increase by 1 more hour, my adrenaline increases by 3. So both of those would be completely acceptable ways. You get to choose one over the other. You never have to do one over the other. But those would be kind of the two ways that would be interpreted. So that's what I was trying to babble about, but without writing it down, it probably wasn't being very clear. But now I have to erase it because I need to put that other thing back. But I'll leave this up for like 5 more seconds. You can always go back to the recording and find it. What time is it? 12:33? Okay. So that's kind of what we're going to do here is we're going to take this kind of idea and we're going to write it in one of these two ways. Whoops, so now I got to erase all this. It really needs to be a just kind of drag and erase kind of deal to erase a bunch of stuff at once because this isn't working. And what did I erase from here? It was f prime of 2 equals dy over dx at x equals 2. So now let's formally do an example. So that was kind of like a quick example that I technically wrote down the answers to, but let's do an official example that we have down here. So say we have this function Q equals F of P, and it's going to give the number of thousands of tons of zinc. I'm just going to start circling our units that we're going to need eventually. Excuse me. Thousands of tons of zinc produced when the price is P dollars per ton. Then what are the units and the meaning of, now that might be hard to see because it's kind of small. Oh man, I meant to fix that to 0.2. This is dq over dp when p is 900, and that's being equal to 0.2. This would be essentially another way of saying kind of like f prime of 900 equals 0.2. You just kind of link the two types of notation we have together. So the first thing I want to do is I want to figure out the units. Well, since I have dq over dp, and again, this is why Leibniz notation is really nice. If you just gave me f prime of 900, it might take me a little while to figure out what the units are. But if you write it as dq over dp, then you can just kind of say, well, what are the units of q and what are the units of p? So our units here, so the units of q, or thousands of tons of zinc. These units for this one are a bit tedious, but we have thousands of tons of zinc, lots of ofs. And then the units of P were dollars. My pen just stops working every once in a while. Dollars per ton. So again, kind of tedious units, but that's what they are. And so now I have to interpret it. And for this one specifically, I'm going to do it in both ways, and then I'm going to just start using one unless someone asks me to use them both. So now I want to interpret this. So say I go with my rate way first. Well, the first thing I have to tell them is essentially the starting x value. Well, here our x's are our p values, so the p value would be 900. So we're going to say essentially after $900 per ton. So after $900 per ton, starting x value. And then you state the y values are either increasing or decreasing. Well, is the slope value positive or negative? We have a positive slope here. So we're going to have that the y values are increasing. Since the y values is an amount of zinc, I would say the amount of zinc is increasing by, so that's kind of step 2. I'm kind of, we got step 1. We got step 2, kind of linking it back to that thing we just wrote down. So n is increasing by 0.2, and then since we're using the rate way, we have to use this entire unit for the derivative value. So it would be 0.2 thousands of tons of zinc per dollars per ton. And again, really strange units on this one, but gets the point across, hopefully. 0.2 ton dollar. So this would essentially be step 3. Does that make sense? I feel like most people use this way, but just in case, I'm going to write down the other way as well. Just for this one, and then again, I'm going to go just to using one over the other, unless someone specifically asks for it. So if we kind of want to use that step way, we kind of start off with the same way. After $900 per ton, we write, that starting x value down. And then we essentially want to say that we increase the x value by 1. So increasing, it's always increasing the x value. So increasing by $1 per ton. So that's kind of step 2 for the step way. So increasing by $1 per ton. And now we essentially tell what's happening with the y value. So is it positive or negative? It's positive. So we're going to say that increases because the slope is positive, the amount of zinc. That's not how you spell zinc. Zinc by 0.2. Now the only thing that's different with this one is we no longer use the entire unit for the slope, we just use the y value unit. So we would just say 0.2 thousands of tons of zinc. So depending on kind of which way you use, will also kind of change the units that you need to write down as well. Let me make that 3 way smaller. 3. Now again, you get to choose one way over the other if you're asked to interpret. I will say on Wiley, I think sometimes they have some drop-down boxes where you have to pick the correct option to make the interpretation correct. And I do think that they can kind of bounce back between the two, so you do want to be familiar with both ways. But if you're just asked, interpret this, say on a quiz or an exam or anything, you just have to do one over the other, whichever one makes you happier. Questions, concerns on that? Okay, let's do, we'll probably just get to 2 more of these interpretation ones. There's one last piece that we might not get to today, which is sad because I hate not getting to everything that's on your homework by Friday, but it just keeps happening. So say the cost C in dollars of building a house that is A square feet in area is given by the function Z equals f of A. What are the units in practical interpretation of f prime of A? So now we're asking for the units of f prime of A. The first thing I would personally do is I would try to write this in Leibniz notation, because again, the Leibniz notation, the units essentially fall right out from it. So the Leibniz notation is always essentially a dy over dx. So what are our what are the equivalent y values here? What variable is acting as our y's? Well, that would be our c, so it would be a dc over a dA. So that would be our Leibniz notation. So if I write down my Leibniz notation, well, then what are my units? My units then would be the units of C, so dollars, over my units of A, which are square feet. So while they didn't ask us for Leibniz notation here, I think just the fact that it makes it so much easier to see what the units are is a good reason to just write it anyway. So now I want to interpret this. Now the thing here is that I don't have any values like the one before, so I can't quite get a formal statement like we just did for the one before it. We kind of just have to write a generic statement because I don't have any starting value and I don't know what the actual value of the slope is. But if you think about what the derivative is a slope. So that would essentially be telling us that if we increase, our x values by 1, however much we'd increase our y values by, kind of going with that step idea as opposed to the rate way, because since we don't actually have a number for the value, the rate way doesn't really transfer over as well. So the interpretation here, if we kind of think about it a bit more in the step way, is that whatever that value is for the derivative, whatever f prime of A is, because that's going to be a number, I don't know what it is, but if I'm given that number, this is going to be the cost of building 1 more square foot on a building that is, now what would technically be the starting value? Again, we don't have an actual number here, but it would be whatever the A value was. So if a building's already A square feet, this derivative value, whatever value it would turn out to be, would be telling us the extra cost of adding on an extra square foot. Does that make sense? So even though we don't have the numbers here, we can still kind of get the idea of that interpretation is telling us how much we're increasing the cost by kind of per square foot, if you will. So I could also think about it as cost per square foot. That would kind of be more the rate way, and that literally, I've never thought to write it that way before. I don't know why I've never thought about that. So it's kind of telling us that cost per adding on an extra square foot. Questions, concerns on that one? We'll do one more. Okay. try to leave that last bit in there while we do part 1 of this next problem. So say we have the time L in hours that a drug stays in a person's system as a function of the quantity administered in milligrams. So L equals F of Q. Interpret the statement F of 10 equals 6, give the units for the numbers 10 and 6. Now be careful here. There's no prime. That's just a regular old F of 10. So it's not a slope. So we don't need those in slope interpretations we were just looking at. But let's think about what this, kind of what these numbers are representing here. So that 10 is a Q value, which is in milligrams. And this 6 is an L value, which is in hours. Now, if we go back and kind of look at the context of this problem, we're talking about how long a drug stays in a person's system. So this would mean that essentially saying if 10 milligrams is administered, oh, that got away from me. And maybe I should even say if 10 milligrams of the drug is administered. Maybe be a bit clear about what is being administered. So if 10 milligrams of the drug is administered, then this is telling us that it stays in their system for 6 hours. But again, that's not a rate interpretation, so we just kind of had to interpret it just in terms of the context that we're given. And now we get on to the derivative pieces. Because now we're asked to write the derivative of the function in Leibniz notation. Let's take care of that first. So Leibniz notation. Well, if we have that L equals F of Q, it means essentially our L acts as our Y value, so we would have DL over DQ. And then we're told if F prime is equal to 0.5, what are the units of the 0.5? So here we just want the units, and then we're going to interpret it in part 3. Well, if I have that Leibniz notation, again, the Leibniz notation makes the units fall out very easily, which again is kind of the reason we're going to use Leibniz notation, is because it makes the units much easier to find. So what are the units of L? Well, that was hours. What are the units of Q? That was in milligrams. So our units of our derivative are going to be hours per milligram. And then say I want to interpret this. So let me just do the right way. At the very end, I can write down really quick the other way if anyone wants to see it, but I won't do it unless someone tells me that they want to see it. So say I want to now actually interpret that f prime of 10 equals 0.5. I should really start putting zeros in front of these numbers. So in our kind of setup, first thing we need to do is tell them the starting x value, which in this case is 10. So we essentially have to say after administering 10 milligrams, of a drug. Well, then I need to tell them whether the y values are increasing or decreasing. Well, this value is positive, so we're increasing. So we would say the rate at which the drug, why did I write it like that? That is not what I should be writing. Go away, notes. So we're talking about the amount of time it stays in their system. Sorry, so after administering 10 milligrams of the drug, the amount of time it stays in their system is increasing since the derivative value is positive. by 0.5, and now we need the units of the derivative, which would be hours per milligram, so 0.5 hours per milligram. We are out of time. If anyone wants to see the other way to write it, just let me know and I can write it super duper quick. Otherwise, you are free to go. We do have one more thing to cover on Monday in terms of 2-3. So there is a small bit that you might not be able to finish in the homework. Once again, I'm really sorry about that. We were supposed to cover this by the end of today. And things are just not going as quickly as they should be this semester. But the large majority of your homework you can do already. And then the very small amount that's left is hopefully not very much to leave for Monday. So have a good weekend. Oh, it's raining. So yeah, have a good day. I'll stop the recording now.